It's winter here. I have to admit, it's really pretty, right? When you see the snow falling and it's covering the trees, it's a beautiful view. I'm much more of a warm weather person though. So I like looking at the winterscapes from indoors. Outside, I don't know. I prefer it warm. Well, as a Canadian, it comes with the territory. You got to live in a place where it does get some heat in the summer, but in the winter, it does get cold around here. I love it though; it's beautiful. You know, uh, like I said, I'm not much of a winter person, but you got to go outside and enjoy it every now and then. So one of the things that I do have fun with doing is tobogganing. Right? It's nice. You get a sled, you go find a nice hill, you walk up that hill, get to the top, look down, get in the sled, and down you go. It's a lot of fun, right? You can get some good speed. I remember it sometimes is scary if the slope is too steep, right? You go a little bit too fast. Sometimes you'll take a tumble, but it's all good fun. You're landing on snow, you know what I mean? As long as you're dressed warm enough, you can have a good time. Of course, that's why it's always fun to take the kids out there too, because the kids aren't really going to get themselves into trouble. They're not going to get hurt. They might take some tumbles if they take a hill too steep, but you'll be fine. You get down, you get up, and you do it all over again, right? The slopes of those hills, of course, the shallow slopes, you don't go so fast. The steep ones, you do go a little bit faster. Hmm, I don't know. Depending on your mood, you might want to choose one over the other. But I think about it. You climb up that hill. You're giving yourself energy, right? It's the amount of energy or potential energy that you have as you get up that hill. And then you slide down and then that energy gets released. And the steeper the slope, the faster it gets released. It's kind of the same way that these old incandescent bulbs work. They require a lot of energy to go up to the top of that hill. And you get to the top of that hill and you slide down. And the steeper the slope, the brighter the light, the faster you go, right? These little incandescent bulbs, like they have a filament inside, of course, if you remember from my last video. And I talked about how they have a built-in resistance. And or I may have talked about it, I don't actually remember, but they do. They have a bit of a built-in resistance, right? And that resistance is kind of like the slope of the hill. A bigger resistance inside this bulb means that slope is shallower, and as a result, you go slower, and the light illuminates a little bit dimmer. A low resistance inside this bulb means that the slope is steeper. You go faster and the light gets brighter. And of course, by the time you get to the bottom of the hill, it's very easy to get up, walk back up to the hill and do it all over again. That's why these bulbs are really easy to run. You plug them into the wall and they simply work. That's one of the reasons they've been so successful. But of course, you don't want them in your house anymore, right? We know that they're wasteful because it's not just light, it's a lot of heat that they produce. And we have better ways to light our homes now. So this was the open LED bulb that you saw me reveal in the last video. And these are a little bit different. It's not the same as walking up to a hill and coasting down on a sled. In fact, these LEDs are not a hill at all. In fact, it's almost like you're walking up towards, I don't know, a wall. Okay, so you're walking flat on a flat surface and then you get to a wall. That wall's not so high, it might be, I don't know, maybe like shoulder level or something like that, right? So it's not like a huge wall. You can still perhaps see on the other side of it, or maybe you just can't see the other side. Maybe it's just above your head. Regardless, it's a small wall, small enough that you can climb over. But of course, climbing over the wall takes some energy. The energy it takes to climb over the wall is arguably less than it takes to trudge up a giant hill. But you do have to spend some energy getting over that wall. Now, once you get over that wall of these LEDs, on the other side of it, there's not a nice, convenient, gentle slope to go down. It's a cliff. It's a free fall cliff on the other side of these LEDs, or the other side of that wall. So it makes it quite different, right? You can't use a sled to go down that cliff. And if you go down that cliff without anything, well, you're gonna fall to your doom. And that's actually how these LEDs work too. If you give them enough energy to get over that wall, and you don't give your LEDs a parachute, they're not going to be happy with that. In fact, they will fall to their doom as well. They're not going to survive putting that energy in. So unlike this incandescent bulb, where if you simply have enough energy, you'd be able to get this thing to light up very easily. These things require a bit more complexity for them to work, right? They need to have some sort of a parachute. And with that parachute, you'll be able to control the amount of energy or current going through these things, or, related to the speed of your descent. So a very large parachute, right, will make you fall slower, and therefore these things will glow a little bit, dim. A smaller parachute means you're falling faster, and these things glow brighter. And if your parachute gets too small, well, eventually you'll go too fast, and you're not going to survive that fall. Same thing with these, right? Too much current, and they won't survive that kind of energy. So LEDs are a lot more complex to run than your old incandescent light bulbs. So if you remember from my last video, and if you haven't seen it, go check it out. I talked a little bit about how these incandescents need an alternating current, or they will work on an alternating current, and these LEDs need a direct current. But just as you heard from my sled story and parachute story, it's not just about the alternating and direct current. These things are a lot more complicated to run, which is going to make our endeavor a little bit more challenging. The good news, though, is that there is no shortage of designs out there, of how to actually do that sort of thing, how to actually put a parachute on these LEDs as you get over that wall. So let's take a look and see what the internet has to say. I mean, isn't that where we start all of our research, right? Let's just go online and see what other people have done when it comes to running their LEDs. Yeah, there's quite a lot. There's a lot of people out there online who have their own ideas on how to run LEDs. So, I mean, that's good for us, right? Because that means that we got a place to start from. So let's there's a few of these circuits that I want to be able to share, but let's start with the most basic one first, right? Because this one, it's really easy and it'll help get across some of the concepts. How about I draw it? And so, well, let me draw it. We can see where we go from there. There you go. That's it. That is possibly the simplest circuit you can imagine, but it's a great place for us to start to look at how to drive an LED. So basics about the circuit, of course, we have our power supply in, there's our return to the power supply, here's our LED, and there is a resistor. So, okay, so I probably couldn't get any more simpler than this, but as the energy comes out of our supply, it's going to encounter this LED. And notice the LEDs kind of looks like an arrow. It's because they can only be plugged in one way, right? So that's why it's drawn this way. It's got to go in the direction of the current flow. So it's going to go this way. And here is where your energy is going to encounter that wall, kind of like where I said before, right? So there's this wall that exists. Then the energy has to kind of go over the wall before it can continue on its way. Now, just like my other examples, when you go over the wall, you're going to hit that cliff, right? We need a parachute. Well, the parachute is right here. This resistor is our parachute. Oh my gosh, I'm a terrible artist. But there's our parachute, and here's our dude who's falling the parachute. All right, so we got our parachute here, and there's a wall. As long as these two things are in play, then we should be okay. Energy comes in, it's enough to get over that wall, and then we got our parachute to slow down our descent, in other words, control our current, and then our energy gets back to the supply, and we should be in good shape, and that is going to light up. All right, well, if we're going to make any more sense out of this, we got to put some numbers onto this schematic for us to see if it'll work. In order for us to do that, well, I have with me here an LED. Now this is just it's a basic LED. It's nothing too fancy. You can find these things all over the place. I'm sure you've probably seen it before. When you get an LED like this, it comes with a few specifications. So this was written in the box where I got it, and let me write those specifications here on the sheet. So first specification is okay. So the voltage. The voltage of the LED is actually a range. It was between 2.8 to 3. If I remember quickly, 6 volts. All right, it had one more specification by the LED was 20 milliamps. All right, let's talk about the first specification. It's the voltage drop between 2.8 to 3.6 volts. This is equivalent to the size of this wall. So a 2.8 volt wall means it's a little bit shorter, and a 3.6 volt wall means it's going to be a little bit higher. It's a range. So we don't know exactly the size of the wall. We just know for this particular LED, it's going to be somewhere in this range. All right, and we know in order for us to ensure that we have enough energy going over the wall, then the supply has to be greater than the highest possible voltage of this LED, which is in this case 3.6 volts. So I think what we're going to do is we're going to give our supply a nice, let's give it 5 volts. I mean, that's a common supply to work with. So we're going to give our supply 5 volts. And that means that it should be plenty enough to get over that wall and then get into this parachute. Now, once our energy goes over this LED wall, so it's going to subtract from that 5 volts, meaning the voltage left over to go through the parachute is going to be somewhere between, well, it's going to be 5 minus 2.8 or 5 minus 3.6. So I think we're going to have to actually do 2 scenarios here. So there's going to be scenario 1. I'm just going to write this in here. Scenario number 1, where the voltage across that resistance, or voltage across the resistor or parachute is going to be 5 minus 2.8 volts. And then we're going to put a scenario 2 over here, number 2, where the voltage is 5 minus 3.6 volts. All right, so that's what's happening as soon as we get to this voltage, and now we can go back to the supply. So now that we know the voltage across that resistor, we can actually figure out the current. Now, in order to figure out the current, I'm going to do some math here, but before I do that, I want to talk about the second specification that came with this LED, this iLED equals 20 milliamps. Okay, what this specification doesn't say, it's not saying that this LED will draw 20 milliamps of power from our supply. Remember, the LED has no built-in resistance. It has no way of determining or controlling the amount of current through it. So what that number actually means is this is the safe maximum current you should be drawing through this LED. You should be. You can go a little higher, but if you go too much higher, you're really eating into the life of that LED, and it's not going to like it at all. It will probably burn out if you go too much higher. It can probably accommodate a little bit more without fear, but really you shouldn't be pushing any more than 20 milliamps through this. You can, however, push less. And remember, these LEDs are current driven, which means that if the more current going through it, the brighter it's going to be. So this 20 milliamps is effectively the brightest reasonable intensity that this LED is capable of generating. Anything less than that, and you're going to get a dimmer LED. So we control this amount of current through our parachute, right? That's why we're interested in figuring out how to size this resistor or size this parachute to control our rate of descent. Do we want a big parachute to try to get our current to its appropriate level, or do we need a small parachute to get our current to its appropriate level? Well, let me do some calculations here, and we'll figure out what that R needs to be for us to get around 20 milliamps. And I'm going to do that calculation for both scenarios. Bear with me a moment while I do these calcs. All right, there you go. So that's the calculations for both scenarios to get us an appropriately sized parachute. So if we want to get 20 milliamps, that's the 0.02 amps number you see here on both of these scenarios. If we want to get 20 milliamps out of this LED, this parachute needs to be sized somewhere between 110 ohms and 70 ohms. Somewhere in between, because we don't know what the voltage across this LED is going to be. So we're going to have to range it in between here to get this proper value of R. Okay, so I mean, that's really all we have to work with. And we know that we don't want to exceed 20 milliamps, but we can certainly go less than that. So because we don't know which one it's going to be, I think it'll be safest to make sure that our parachute is at least 110 ohms or bigger. And that's going to allow us to ensure that we have the best, safest running LED possible. All right. So I think the next step is to build it. Let's put it together. There you have it. Pretty simple build, right? But that's basically it. We have our power rail at the top here. It's going to go through this black lead down to the LED, which is over here, and it's going to continue and pass through the LED, back through this resistor, and back to our supply. Okay, so first thing you notice, this resistor is not 110. I don't actually have a 110 ohm resistor. So the closest thing I could find was a 200 ohm resistor. And that's what this value is here. This is actually a 200 ohm resistor. And so if I do just quick math in my head, at 200 ohms, we'll probably get about half the intensity that this LED is capable of producing. That's okay for our test. We just want to make sure that this thing actually works. So we're going to run this at 200 ohms. Let's turn it on, or let's supply the power and see if this thing actually works. Let me get my power over here. So we're going to supply 5 volts to the circuit. Look at that. Our LED lights up. Great. So we have this LED lit up, and one of the things we can do is we can actually test this now using a scope to see where in this range our LEDs actually landing. So let me do that. I'm going to get a scope set up over here. Just get our leads in, and okay, so I got my scope. Connect the ground, so it's a shared ground. All right, and let me turn the scope on the screen so you can actually see, follow along and see what's going on here. There we go. Okay, so we got our scope, and right now I'm putting the mouse pointer right where the value is of the voltage is reading. Now it's really low right now. It's around 2, hovering between 2 something millivolts. It's not connected. So this is just parasitic readings that it's getting. First thing I'm going to do is I'm going to take a look at our supply. So I'm going to put our scope right at the tip over here of the power in. And we can see what voltage we're getting. Look at that. That looks like 5.02. So yeah, 5 volts coming into our supply. It's exactly what we'd expect, right? 5 volts in. And now, so what I did is I'm actually scoping here. I'm just going to use this pencil so you can see where I'm scoping. I'm applying the scope right over here. And so you'd expect this to be 5 volts because we're giving a 5 volt supply into the system, right? Next thing I'm going to do is I'm going to scope on the other side of that LED. So right over here, I'm going to put the scope on there. And the reading shows 2.2 volts. Hey, that's pretty cool. So 2.2 volts, that's exactly the same reading that I got over here. So that's telling me that the voltage drop across this LED is 2.8 volts. We're right on scenario number 1. It's kind of cool that it landed right at scenario 1, and we have a 2.2 volt reading right at the other end of this LED. So that means that we're basically pushing, well, we're not actually pushing this value because we're not using a 110 ohm resistor. We're using a 200 ohm resistor. So we're probably pushing about 10 milliamps, maybe about 11 through this thing right about now. But that's pretty cool. We landed right at scenario 1. So that's really neat. Okay, so we have this LED circuit and it's working, but it's not going to work for us long term. There's actually going to be a bit of a challenge here. So let me bring this back. I'm going to turn the scope off. Okay, so we got a few challenges with this, right? One, this LED that you're looking at here, this is an indicator style LED. It's great for lighting something up to, look at some sort of an indication. It's not that good for lighting up a room. I mean, this intensity is really, really low. First thing we're going to need to beef up the power that's going through this, right? So we are going to need something a lot more powerful to run if we're actually going to start lighting up a room, right? There's a few other things that are wrong with this as well. One of the more obvious ones is the fact that, well, we were lucky that we landed on scenario 1 and we ended up at 2.2 volts. If, for example, we landed, let's say this LED was different and the voltage drop was closer to 3.6, well, that would mean that we're actually getting a smaller voltage at this point. And what that means for us is that the intensity will be different. So we have no control over where this voltage lands for this particular LED. And so we're really at the mercy of the manufacturers, and that's not good, right? That means that the intensity will not be controlled as tightly as we want it to be. And hey, we're building illumination lights here, right? So we want to be able to control that intensity. I don't want to have such uncertainty there. So that's one of the reasons that this is not going to work. Here's another reason. Let me turn the scope back on. And okay, so I'm going to put the scope right at the point it was before. Okay, there we go. So we're reading 2.2 volts. Now watch what happens as I adjust the voltage. You're going to watch the scope, but also look at the LED. There. So you can see my value going up and down. My scope is going up and down. Here's going up, here's going down. And look at the intensity on the LED. It's getting brighter and dimmer, right? So here's another thing that's not so good. If we were dependent on the voltage on this circuit, any change in the voltage is going to change our intensity of the bulb. Again, not something we necessarily want. It's going to cause us a problem. All right, so there's a few reasons we can't go with this one, but let me talk about the first one. The first thing I talked about when it says I need some more power out of this. If we're going to get more power out of this, first of all, this LED is limited to 20 milliamps. We're definitely going to want something a bit bigger. So here is one of those bigger LEDs. This LED here, it's the voltage range is probably around the same. I actually don't know what the voltage range of this is going to be, but the current that can pass through this LED is a lot higher. This one is supposed to be rated at about 350 milliamps. That is going to be a whole lot brighter than this right here. But if we're going to be running this 350 milliamp LED, it's going to change something. Remember, that current has to go through that LED, but it's also got to go through this parachute. These resistors here have a limit to how much power they can handle. Bear with me while I do a power calculation of the power that's going through the system right now and what we can expect if we're going to run this kind of voltage through. Okay, let me just do that calculation quickly and see what's going on here. All right, there's the calculations. So what I wanted to do is calculate the power through that resistor under both of these scenarios. And we know we're closer to scenario 1. So right now the power going through this resistor is about 44 milliwatts. Under scenario 2, it will be a little bit less, around 28 milliwatts. This particular resistor has a power rating of about 250 milliwatts. So these are well under the limit of this resistor. So both of these are running just fine. This circuit is quite happy. If, on the other hand, we try to put this high current LED into this circuit and try to run 350 milliamps through it, well, the power through that same resistor is going to be around 770 milliwatts. So if I try doing that, it's not going to be very happy. In fact, it would probably burn, very likely burn. It's well above the power rating of this resistor, and it won't be able to handle it. So we're going to need to change our circuit if we want to be able to run a beefier LED and get a brighter illumination out of it. We're going to have to do something, either change this resistor or do something more. Luckily for us, there are some options. Let's take a look at something else. All right, so here's another design I found online. And I gotta say, it's different. Frankly, it makes my head hurt a little bit. I can't pretend to know, or I can't pretend to say that I truly understand what's going on here. But let's take a little closer look as to what is actually happening here. So our current is coming in through the resistor or through the LED just like before, but now rather than going straight to this parachute resistor down here, we have to go through this transistor, and that transistor is behaving strangely because it's got another transistor kind of not quite back to back, but they're in an interesting configuration. It's such an interesting configuration that if this, let's assume this transistor is conducting, right? And so that means that there is current flowing through this LED and into this resistor point here, which means that there should be current flowing this way as well. And if there's current flowing this way as well, well then this point over here will be grounded. Therefore, there should be no current flowing through this way. So basically what we're saying is if this thing is conducting, then this transistor is going to force this to stop conducting. And then if this thing is not conducting, then this transistor will also be non-conducting, which means that it's going to cause this transistor to conduct. So it makes my head hurt thinking about this, but these two transistors are fighting with each other. They're both like, I want you to conduct, and they're both like, I want you to stop. They're both telling each other to either conduct or not conduct. And there's going to be an epic battle between these two transistors. And the mathematics to try to figure out which one is going to win, I don't know. I think it's far too complicated for me to understand, let alone get into this video. So I'm just going to not get into the mathematics here. But and you know, A, because it's complex, two, because I don't even think I understand it fully. So I won't be able to get into this, but I can clearly see that there is some sort of a feedback mechanism happening here that's going to cause these transistors to both find some sort of a compromise and settle somewhere. Okay, so like I said, this is tough for me to understand, and I was able to find another circuit which is actually very similar to this with one small change. Let me show it to you so you can see what this is. I'm going to turn this screen off. Get back to the other one. All right. Ta-da! Look at this. So this is the other circuit. It's very similar to the one we just saw. The only difference being that over here where Q2 is, this is now a MOSFET. Whereas in the previous circuit, this was a transistor. The reason this is easier for me to grasp is because a transistor is current controlled. There's current going in. There's actually two converging current paths through a transistor, one going down here and the other one coming across here. Whereas with a MOSFET, there's no base current. There's no current going through here. A MOSFET is voltage controlled. So for me, this is far simpler to understand. I know that with this circuit, because there can be no current going through this path over here, the only places where the current can flow is obviously down through this resistor and then down through this transistor, if of course it's conducting. Another place that the current can flow is through this LED, through this MOSFET, and down through this resistor. There's also going to be a tiny current flowing this way through the brace as well. But right away, there's only three paths of current, three possible paths that the current can take through the system, whereas the other one, it was a bit more complicated. So for me, this is easier to understand. Another thing that makes this easier to grasp for me is the fact that because of the way this configuration is with this resistor down here and this transistor, this voltage point right here at this resistor, it's pretty much fixed. Now, if that voltage point is fixed and unchanged, regardless as to how much current flows through the system, well, then that means that I have very good control over the size of my parachute. Remember, this resistor right here, this is equivalent to the parachute in our previous example. This resistor, here, let me bring it back, and that resistor serve the same function. They both serve as the parachute. But this time, I have much more control over the size of my parachute because the voltage is very constant. That is great for us. I'm going to be able to control this a lot better. The rest of this, what is this voltage going to be at? Well, because of that feedback mechanism, it's going to be somewhere. I don't actually know what it's going to be right now. I'm sure the mathematics can tell us, but like I said, I'm not going to get into the math at this stage. We can figure this out. In fact, we can test this. We can build this and see what that voltage is going to be. And in fact, that's probably the best way I'd like to be able to do this. I want to be able to build this. And I'm going to build this with, not with the old LED that we had. I'm going to build this with the bigger LED, because as we're going to find out, because of the way this thing is configured and because of the way that the voltage across this R is not only known, but it's also very small, we're going to be able to run this LED safely with this resistor. All right, so I'm looking forward to this. We're going to build this in the next video. So if you haven't subscribed yet, please do. And as soon as I release that next video, you'll be notified and you can watch us build this. All right, until then.